So now the question is, once utilities know or think they know what demand will be, how do they pick what kind of power plant to build? So we've talked about at least one way to make this decision based on economic considerations, which would be net present value. We've talked about how net present value can be used to give single numerical scores based on their expected discounted cash flows to alternative investments. So we could look at one type of plant to figure out what its net present value is, look at a different type of plant, figure out what its net present value is, and whichever one has the higher net present value, we might consider to be the better choice. Another simpler way to look at this is actually to use what's called the levelized cost of electricity. And so there are lots of flaws related to using the levelized cost of electricity in terms of deciding what new types of power plants to build. And we're going to spend an entire lecture talking about the levelized cost of electricity and its flaws in a couple of weeks. So it's the price in dollars per megawatt hour that a power plant would have to sell its entire life to pay for itself, to pay for its operational costs, its variable costs, as well as its fixed costs, including the mortgage payment on all the debt that would be required to build the power plant. And so we can look at different generation technologies here in order to compare them. The most expensive here is solar thermal, so that's not the same thing as solar photovoltaic. And then offshore wind is pretty expensive too. You see solar PV. And then all the way to the right, we see some cheap stuff. Onshore wind is extremely cheap. Natural gas, combined cycle power plants, as well as geothermal. So power system planners could certainly look at the levelized cost of electricity for different types of power plants and just pick the cheapest ones. Is it that simple? No, it's not, of course. Otherwise, why would I ask? So let's sort of pick holes in that theory that utilities should just use the cheapest type of generation possible and build as much of that as they need in order to fulfill future electricity demand. So the cheapest possible generation here is actually listed as geothermal. So can utilities all over the United States build geothermal? No, unfortunately, geothermal potential in the United States is very geographically limited, at least conventional geothermal, to places out in the Mountain West. Okay, so we know utilities in North Carolina aren't going to build geothermal, but what about onshore wind and natural gas advanced combined cycles? These cost about the same, so why not just build wind power all the time? We know that there are emissions benefits associated with wind power. There's no carbon emissions at all, so why not just build wind turbines instead of natural gas combined cycle power plants? Well, the question is, we don't know if we can really count on wind all the time. Wind is a source of variable renewable energy, which means that when the wind's not blowing, we're not producing any electricity. And so depending on where we are in the United States, that means on a year-to-year basis, the available amount of wind power could change for the exact same wind farm. There might be seasonal effects. In other words, during certain parts of the year, wind power may be plentiful than others. And then, of course, during the day, there are certain hours of the day when wind may be more active than others as well. And so this figure shows you some of that. On the y-axis here, you have capacity factor, which is essentially a measure of the percentage of the installed capacity of a wind farm that's actually being used to produce electricity. So 1 would mean that a 500 megawatt wind farm is producing 500 megawatts, and 0 would mean that it's producing 0. And the different colors show you the statistical uncertainty about how much wind power is actually being produced from this project. So the black line is the median, right? It's the 50th percentile. If we assume that this was a normal distribution, then that median line would represent the average wind power production from this power plant. So what we see here in that case is that the wind farm could produce a lot more than an average throughout the year, but also a lot less and close to 0 on some days as well. What that means is that future generation from renewables, wind and solar and even hydropower, is uncertain. And so we can't consider it by itself to be firm or guaranteed capacity that would help us meet peak system demand. In other words, we can't be sure that in the hottest hour of the hottest day of the year, our renewable energy is going to be producing electricity. And so, what utilities and system planners will typically do is they'll come up with a ratio to downgrade the ability of renewables to help meet peak system demand. For example, a utility might say for every 1 megawatt of wind power capacity added, it helps meet 0.4 megawatts of peak system demand. And what that means is that you would have to add a lot more wind power capacity than you would natural gas generation if you were trying to meet peak system demand. So this kind of brings up another question, which is, do we always have to build something new to meet future electricity demand? And the answer increasingly is no. There are other options for meeting peak system demand apart from building new capacity. And one example, which is one we'll talk more about later in this class, is demand response. And so demand response is a change in a customer's electricity consumption due to some sort of explicit request from grid operators. And so usually when the customers reduce their electricity consumption, they're rewarded financially. So one example might be programs that sign up customers, residential electricity customers, who are basically volunteering to allow the utility to adjust the power consumption of cooling appliances or HVAC units in the summertime. Other examples might be slowing down or stopping production at industrial operations or dimming or shutting off lights. And so Duke Energy has programs like this that cater to both residential customers and commercial customers. And it allows them to volunteer to have Duke curb their electricity consumption during certain periods of the year. And the reward is you get some sort of incentive, some percentage off your monthly bill. And so increasingly, demand side participation is being viewed as a resource that can help meet electricity demand in the future. You can imagine that if just one person decided to volunteer to allow their electricity to be shut off during the hottest part of the summer, that might not make such a difference. But if thousands and thousands and thousands of people volunteered to have their electricity shut off just momentarily during the hottest part of the summer, that might make a lot of difference. In other words, it would give the system the ability to sort of push a button and reduce electricity demand, which is a lot like pushing a button and producing electricity. And so this type of resource is actually becoming an accepted way to meet peak system demand in different power systems. And so what this figure shows, and this is a figure from PJM interconnection, so a deregulated electricity market, the one that starts at the border of North Carolina and Virginia and goes up to New York and across to Chicago. This shows the increase over the last several years in the capacity of demand resources, specifically demand response and green, that are being accepted as contributions to help meet peak electricity demand in the future. And so we're going to talk more about demand response and demand side management at a later point in this class. So public utility commissions often require that utilities make their long-term 15-year plans public about what new capacity they are projected to need, and also what their possible choices are of what types of plants they're thinking about building. And these plans, which you can look at online, are called integrated resource plans. So for example, here's a figure from Duke Energy's most recent integrated resource plan. This talks about the different types of generation that Duke thinks that they're going to build in the future. And you can see from this pie chart, most of it is projected to come from new natural gas power plants, about 66%. 30% is expected to come from a combination of renewables, demand side management, which would be demand response, and energy efficiency. And then a very small percentage of it, 4%, is expected to come from energy storage. Now, interestingly, this is a plan that incorporates a cost of carbon. So in other words, there is not a carbon tax in the United States, but Duke Energy is already sort of charging itself a cost of carbon on the order of $17 per ton that starts in 2020 and escalates to $36 per ton by 2040. And so it's not actually taxing itself, but it is assuming that a cost of carbon is in place when it's making decisions about what new types of power plants to build. And so, what is noticeably absent in that pie chart, of course, are coal plants. Coal plants are not being considered by Duke Energy, or to my knowledge, by basically any utility in the country anymore. And that's because utilities expect there to be some sort of penalty for carbon at some point in the future. So that's good news, and we'll talk more about this throughout the rest of the semester. But be careful in your interpretation of this. This doesn't mean that Duke is retiring all their existing coal plants. It just means that they're not planning to build new ones. Okay, so that's it for this time. Next time, we're going to talk about short-term operations at electric utilities. So see you there.